All right, good morning, folks. I'm Al Rizzi. I'm the Chief Scientist at Boston Dynamics, and I'm very excited to be chatting with everybody today. We're going to talk about, our version of mobile manipulation and the ARM that we're going to be making available on Spot Robot and the interfaces to it. Joining us is Andy Barry, one of the lead engineers who's been doing a lot of work associated with this. Andy, you want to introduce yourself?
Yeah, hi everyone. Really excited to be here and share all the hard work we've put into Spot and its ARM with you guys.
And just in terms of logistics, if you have questions during the presentation, please use the Q&A function in Zoom to get those submitted. We have a couple people moderating for us who will let us know about those questions, and we'll either get to them during the talk or we'll have an extended period at the end of the talk to go over questions specifically. And then as a reminder, we are recording this whole presentation and we'll make it available afterwards. Please don't record it separately. And I think on that note, we're ready to go. So what is mobile manipulation and how does it relate to Spot? You know, the real goal here is to enable Spot to reach out, touch, and interact with the world in meaningful ways. Being Boston Dynamics, we're trying to do that in a way that really looks like supervised local autonomy. And that's really similar to how we've delivered mobility on the robot so far, in the form of something that, from most people's perspective, just works, right? The commands you give the robot are relatively high-level instructions about where to go, and it deals with where it places its feet and how it balances. Similarly, for manipulation, we want to tell the robot what to do, not how to do, as a user, and then rely on the robot to interpret the details of that and use its sensor information to successfully accomplish those tasks for you. The initial release of the hardware and the software that we're going to be providing starting in the spring, or in January, I guess, is really focused on teleoperation and a core API for the ARM. It enables manual remote operation and experimentation with the ARM, and it provides an API that will allow you as developers to build applications around all of those capabilities. And just to be clear, you know, the functionality that we use in order to provide the remote operation, the teleoperation that we'll provide through the tablet interface, is the exact same interface that's provided over the API. So as a developer, you'll have access to all the same capabilities that we have access to. So let's talk a little bit about the ARM itself. So the ARM is a 6 degree of freedom device with a gripper on the end of it. Total mass of the ARM is about 8 kilos, and it's just under 1 meter in length. In terms of performance, it's a rather performant ARM. End point speed peaks out at about 10 meters per second. The ARM has a 5 kilogram continuous lift capacity at about half a meter of extension. I think our lift at full extension is around 2 kilos. The gripper on the end of the ARM has about 130 Newton clamping force at the fingertip. There's an integrated 4K RGB camera in the palm of the gripper. There's also a depth sensor integrated into the palm of the gripper. And there's an add-on port available with the gripper that provides 50 watts of power, GIGI network interface into the internal robot network, and pulse per second interface for timing or sensor synchronization for any devices that you may want to add out towards the end of the ARM. So how are we delivering Spot in the ARM? The ARM is really a fully integrated component with the robot. Because of that, it needs to be serviced, attached, and removed by Boston Dynamics. Control of the ARM really is fully integrated with the robot. And as I mentioned already, you know, there's room to add additional sensors under or behind the ARM, either at the gripper or on the body of the robot itself. In this particular picture, you see a rendering of Spot with the ARM on it, with Spot Cam attached in the rear position of the robot. And then I believe we have a compute payload tucked up under the ARM. So that's a relatively fully configured version of the robot with an ARM. What I'm going to talk about is really the set of behaviors that we're delivering in this initial release with the ARM. And there are a bunch of them that are really targeted at making the ARM useful, both in terms of initial application development and experimentation. So there are behaviors related to grasping, semi-autonomous object manipulation. This is for, touching things like valves, switches, levers, drawers, cabinets, doors. We do have the Boston Dynamics door opening behaviors integrated in this release of the software. We have a relatively well integrated tablet UI that provides access to all of those features. And then we have the API that I already mentioned briefly that really provides a programmatic interface to all of those features and will, for all the developers in the audience, give you access to building your own applications or autonomy systems around all of those capabilities. So being Boston Dynamics, we like to spill the beans. So this is a short video that basically gives you an overview of all of those capabilities. So you saw the robot open that door, walk through that door. We're going to walk over to this switch box, do a little bit of interaction through the tablet to specify where the switch is for the robot, and then semi-autonomously go ahead and grasp that switch over to what we will call a constrained manipulation mode. It allows the robot to actually actuate the switch and turn the lights on in the space. And drive the robot over towards an open space on the floor. Use some off-robot machine learning technology to go find an object on the floor. That in turn interfaces with our semi-automated grasping tools, so very easily makes it possible to hook up that kind of machine learning to grasping that allows you to pick an object up, drop it in the bucket on the back of the robot. There's a quick demonstration of that 4K camera in the gripper being used to inspect this leaking pipe, dripping the Simpsons radioactive goo. We'll go drive the robot over towards the valve on that pipe, again using these grasping tools. In this case, one that allows the user to be a little bit more precise about exactly how I grasp an object. We're going to go ahead and grasp the lever of that handle. And we'll talk about all of these in a little bit more detail. Again, we'll go back to that constrained manipulation subsystem and say, hey, we're going to turn a lever on a handle. We'll actually turn the lever and stop the dripping. Leak solved, world saved, robots are great. And ultimately, we just continue on. So that's really, we're going to talk about each of the components in that video as we go through this presentation, and hopefully give you a sense of, how we make these capabilities available to you and how you can take advantage of them. So first, let's talk about the grasping functionalities. There are basically two types of grasping that we support out of the box with the robot. There's what we'd call pick up an object, which is a relatively automated system where basically you tap on an image and then the robot goes ahead and uses all of its onboard sensors to go identify a graspable object at that location. And then go ahead and quickly grasp that object. So this is exactly what was used to pick up that piece of trash off of the floor in the case there. Rather than the user tapping on the image, we relied on the ML system to identify the location in the image where that object was, and that served as our tap, as you will, for where the robot should go ahead and grasp the object. In the images here in the top half of this slide, you can see us interacting with a laundry basket with some random stuff thrown in it. In the left image, you see the red circle where the user specified, please grasp here. And then in the right image, you can see that the robot is actually able to go ahead and grasp that object. The second version of object grasping is what we refer to as the grasping wizard. And this is useful for being much more explicit in terms of specifying the details of the grasp that you as a user would like the robot to achieve. It's actually possible to fully constrain all 6 degrees of freedom of the grasp that you want to achieve using this system. And this is really useful for doing things like interacting with switches and valves where you want to be very precise about how you actually grasp the object. And we'll go into this in a little bit more detail in the next couple of slides. And again, both of these modes are both supported on the tablet and through the API. So here's an example of that simple pick an object interface. So the first thing we're going to do is pick up a stick off the grass. So there's no prior model, obviously, for the objects that we're picking. Really what's happening is you're tapping on that image. The robot is going and looking at that location in the world and doing its best to figure out how to close the gripper around whatever geometry it sees there in order to secure the object, and it'll happily pick up a stick. Just as well, we can pick up a water bottle off the pavement, maybe a little bit more expected and traditional. We can go ahead and pick up all sorts of random objects. So here we have a pipe fitting and a couple of shoes that are laying around. And again, the robot's sort of picking the best, solving that optimization problem to figure out how best to deploy the gripper in order to grab the object. And ultimately, after we get everything into the basket, pick everything up. We're shortening the video by skipping the act of dropping everything in the basket. Just as I showed you in that previous slide, we can actually go grab the laundry basket. So the nice thing about this system is, again, there's no prior models required. This whole system is basically independent of detailed target geometry. The grass planning happens on robot. And in fact, there's actually some automated tracking of the objects as the robot moves in to grab them. The second version of grasping is this grasping wizard, which is significantly more precise in terms of what it allows you to do. So let's again segment out of that first video we showed you. And this is for doing this precise grasp. So what we do is we take you through an image-based sequence of specifying the actual grasp. So if you watch the video closely, the robot walks off over towards the quarter turn valve. User clicks, hey, this is the thing I want to go interact with. Robot moves the gripper to be close to that object, presents the imagery from the gripper to the user. The user is then able to, in the coordinates of those images, specify exactly how to position the gripper relative to the object, how to orient it relative to that object, and then finally, exactly how close to move to the object before closing the gripper. And the last step is, again, semi-automated to minimize the burden on the operator and improve reliability and robustness of that step. Okay, so that's it for basic grasping. Well, once you start grasping things, you'd like to start manipulating things. One of the things we're very eager to allow you to manipulate are doors. And so, again, there are two versions of our door opening system. The first is basically a fully automated system, and that's the first thing I'll show you. And it relies on you as the user, again, either through the API or via the tablet, specifying a little bit of information to help the robot understand the task that it's trying to accomplish. In particular, what you do is tap on the doorknob in the image, which gives the robot a clue about exactly where to look for the doorknob. And then you tell the robot where the hinge of the door is, basically letting the robot understand if it's a left or right-handed door. After that, you basically get to sit back and watch the robot do its thing. So here's a video of that in action. So we touch on the door handle in the image. Robot will move close to the door handle, deploy the arm. It'll use the sensors in the gripper in order to actually engage the door handle. And then it'll actually pull the door open. As it pulls the door open, it automatically takes care of the problem of blocking the door, reaching around the door, in order to get it to swing reliably and then traverse the door. So the only interaction here was actually at the beginning when the user specified the location of that door handle and which side the hinge was on. The second version of this is sort of a semi-automated version where you can use the grasping tools that we already described to go ahead and engage with the doorknob and then basically warm start the door opening behavior in order to automatically traverse the door. An important note is that all of the underlying locomotion and obstacle avoidance capabilities that you're used to with the robot are actually still running while we're doing door opening. So in this bottom video, you see the robot negotiating over this small platform that's in front of the door. You see us putting a couple boxes in its way as it goes to traverse the door, and it just deals with So it's really well integrated into all of the capabilities that you're used to with the robot. The next set of capabilities we have relate to dragging objects. So whenever you want to manipulate something that's significantly beyond the payload capacity of the arm to actually pick it up, we can actually do that. Again, we use those same grasping tools that I already described to engage the object. And then once you do that, you flip the robot into this dragging mode, and we can actually drag relatively heavy objects. So you'll drag a bench from our old office down the hallway here. You know, the important thing here is that the robot is automatically adjusting for the external forces that are being produced by that object that's dragging. As a side effect of that, you know, this only works as a pulling behavior. We can't actually push things because we're really treating the arm a bit like a robot. And there's no direct control of the end effect or the end effect is really just reacting in order to keep the look well aligned between the body and the object. Similarly, there's no explicit collision avoidance going on in this system. So, you know, if you drag the object into something else, we're not going to take care of that for you at this point. Okay, next up is constrained manipulation. This is that ability to interact with objects that have some kind of constraint already in the environment. So valves, levers, drawers, cranks, all of those things that you might be interested in actually interacting with fall into this category. Again, we use those same grasping tools in order to interact, to initially engage with that object and make contact, and then flip into the constrained manipulation mode where you as the user are able to control the speed and force of the interaction, while the robot takes care of basically automatically tracking the motion, ensuring that it's not pushing in some excessive way against the constraints that are present in the task. So here's an example of with crank. So we select the crank mode, and then once we do that, it's simply a joystick motion to control the speed at which we actually turn that crank. And the robot's taking care of basically not pushing laterally against the crank. And this is, you know, we think this is a really useful feature for simplifying the interaction of the robot with the environment around it, right? It relates to a whole bunch of capabilities and tasks that we think are likely to be useful in a variety of settings. Finally, as I mentioned, there's this 4K camera that we've embedded in the gripper of the robot that's relatively useful for performing inspection tasks. It's integrated in the tablet in the form of a display functionality, and we expect to add additional integration of this camera in the robot as we move forward. Again, useful for remote inspection tasks as well as setting up some of those grasping tasks as I described earlier. And you can just see the integration of that imagery with the tablet in this short video. All right, at this point, I'm going to hand things over to Andy, who's going to talk to you folks about the API.
Yeah, thanks, Al. So we're really excited to provide an API that will allow some of you guys to build some really exciting and interesting applications with the robot. So as Al said, the tablet communicates with the robot over this API, and our goal is to basically give you everything the tablet can do, you should be able to do over the API. We're not quite perfect at that yet, but we're pretty close, and I think you guys will be satisfied with that. And in addition to what the tablet can do, there's a lot of functionality in the API specifically designed to allow autonomous applications and other types of control where you're not running joysticks. So to start with, you know, the kinds of things you would expect for an ARM API are there. So there's general position and velocity control. We support trajectories, those kinds of things. We're also supporting a gaze control, which we found to be really useful to point the cameras in the hand at a variety of objects when you want to look at things. We are going to provide joint control over the API, but this is not going to be 1,000 hertz joint control that you might wish it was. But I think it will still be very useful to a lot of folks. And there will be force control provided over the API. We also had a question in the Q&A about the force torque sensors on the arm. The joints do have force torque sensors on the arm, and we do provide that information out. In addition to letting you, of course, provide force control inputs, and we'll act on that. Next. So one of the things I'm really excited about getting out into your hands is our pickup API. And the main call that I think most people will like is we allow picking an object in an image. So this is basically you provide the XY pixel location of the thing you want to pick up. And you provide calibrated camera parameters. So if you're using one of our cameras, you just copy our structure over. Or if you're using your own camera, of course, you have to calibrate it. And then we'll just go pick that thing up. And we're going to also provide a few other methods, including like pick at 3D location and a variety of things, where if you're doing perception independent of our system, you can inform our system and use the rest of our pipeline. And as Al mentioned, but I kind of wanted to highlight here, if you go ahead and play the video, there's some really neat ML integration opportunities here. So this is really a pretty standard bounding box detector, right? It's not really doing that much special. And all we're doing here is taking the center of the bounding box and passing that into this pick object and image function. So there's a really nice connection between a whole variety of options here to allow the automated grasping system to work for you. Let's go to the next slide. And one of the things, we were building these kinds of autonomous applications, and we realized that sometimes just picking an object in an image isn't good enough, because you as the programmer or as the user have prior knowledge about how you want the robot to pick that thing up. So we're going to supply options that let you say, I want to grasp in this particular way. So Al, if you click once, right, this is a coffee mug, right? And you might say, oh, the automated system might say, hey, the best grasp I can find is from the top. But obviously, if the coffee's full of coffee, you don't want that, right? So you want to grasp on the handle. Click again, Al. And this is, of course, the grasp you want. And so one of the things you can do is you could say, hey, I want the grasping system to solve the whole thing, run feedback, all of that. But I want the grasp to be near this particular 3D rotation. And that's great if you know that 3D rotation, but almost always 3D rotations require you to do some work online. So we're offering a second set of constraints. If you click one more time, which I'm calling vector alignment. And this is actually really neat. It lets you say, I want the gripper to, the y-axis of the gripper to be aligned with the gravity vector, say, in this example. And the thing that's really interesting about that is it lets you as a programmer put in this prior knowledge when you're writing the program. Because if a coffee mug is on a table, you always want the y-axis either aligned with gravity or completely 180 from that, right? So we're trying to allow you to bake in this prior knowledge for your application and avoid having to do a bunch of complicated perception online. So I'm really excited to see what the folks in this room can come up with to build with this. Next. So another point here I wanted to talk about is collision avoidance. If you've used Spot in the past, we've worked really hard on our collision avoidance with the body. The ARM is not going to ship with collision avoidance with the world. So the ARM does ship with collision avoidance with the body of the robot and with payloads you have mounted and informed the robot about. There's a little asterisk there that's not going to be supported in joint moving mode. but we are not going to ship collision avoidance with the world in this release. We do have a force limiter running on the robot. So if the arm starts exerting a large force on the body, we'll start to tone down whatever you're asking for so we don't knock the robot over. But I think it's important to realize, right, Spot is an industrial robot and it's not designed to be used within 2 meters of people. And in some sense, the arm extends the reach of the robot, right? So you as users need to be careful that you don't end up in a situation where you're close to the robot with the arm active. Next. So I think at this point, we're gonna take some questions and hopefully have a nice discussion about some of the applications people are excited about. So we'll let this video play and we're gonna start going through the questions on the Q&A in Zoom. So go ahead and ask there. So I'll take a couple questions we had earlier first. The question is the ARM IP54 rated or more? The answer is we are working towards an IP54 rating, but the initial release of the ARM will not ship with that certification. So we're calling it water and dust resistant, and we hope to go to IP54 at some point, but not in the initial release. Okay, next question was on ARM force torque sensors in the joints. Yes, the ARM has force torque sensors in all of the joints except the gripper. And estimate for on per motor current for you there. Okay, let's see. For some fine-grained manually controlled manipulation tasks like crank control, how much latency is there between control command and execution? Can Spot be effectively teleoped over the network for these tasks? The answer is, so I think what you're asking about is this kind of, if you use the constrained manipulation, we're going to kind of help you there. But if you're using the tablet, there's still some latency, but that latency is relatively small. You can definitely do in the loop control. It of course depends on your network, if you're on Wi-Fi versus directly wired into the robot.
So Andy, if I can cut in on that one for just a second, I think, the key issue there is going to be network latency. So it's very much going to depend upon the particular radio environment you're operating in. Our intent is that things like this constrained manipulation mode and these semi-automated grasping features reduce the need for the user to directly control those types of interactions, that you can in fact rely on local control and autonomy on the robot to actually execute that part of a task for you. And so that's how we think we really come at that problem in a way that's a little bit structurally different than what most people are doing with teleoperated robots.
Let's see. Okay, next question. Can you define your own behaviors similar to your turn crank, or are these pre-programmed? Right now, in the constrained manipulation section, we're offering a variety of pre-programmed things. And for your own behaviors, you would want to use the rest of our API and do feedback that way. And as Al said, if you have a computer mounted on the back of the robot, you can be direct into the robot's network and have quite low latency there.
Yeah, and I would just add to that again, I think, the set of features we're providing in this constrained manipulation mode, we think are pretty exhaustive. We think it's basically any way you could touch the world and want to move something. If you have an application that doesn't fit one of our existing models, please tell us about it, and we'll be happy to look at whether it's easy enough to integrate, because the underlying tooling there is really very capable.
We have a question about can the ARM work on Spot Explorer or Enterprise? The answer is the ARM will work on both models, both Explorer and Enterprise. When is the ARM first released? Al, I think you said something about that earlier.
Yeah, so the ARM is scheduled for release in early next year, early 2021. We'll be doing, the formal sort of, the arm is available announcements at the end of January. And then the exact ship date is still to be determined. We are shipping some early arms to a few early adopter customers, sort of on a beta program basis. If you are very interested in getting early access, please go ahead and contact our sales team at sales@bostondynamics.com, and we'll see if we can accommodate your needs.
Next question, does the ARM consume the use of the front DB25 port? No.
No, it doesn't. We have a separate dedicated port for actually attaching the ARM.
Let's see. Is there any reason that only BD could assemble and disassemble the ARM on the robot? Sometimes you have applications where you do not require the ARM and don't want to sacrifice the 8-kilogram payload. Maybe Al can speak to that.
Yeah, unfortunately, at this point, the ARM is going to be a Boston Dynamics service required feature to attach or detach, and that relates to some calibration and integration issues that are sort of part of how we deliver the ARM in such a fully integrated way. That's something that we may be able to consider in the future.
We've got a question about Choreographer. Al, at launch, will Choreographer fully support the ARM?
I believe the answer is yes, that the ARM is fully supported in Choreographer. There are things you can, there are more ways. If you're currently using Choreographer, there are ways you can cause your robot to fall over or do funny things. Adding the ARM expands the number of ways you can make things like that happen.
We have a question about, are these features available in an auto walk mission?
Not at initial release. That's sort of one of the things we're expect to make available in the upcoming releases. So please stay tuned. We think the ARM is going to be very useful for autonomy in the long term, but we're very eager to get it into your hands and figure out exactly what you want to do with it early on. So we've limited the initial integration to tablet and API and not to the auto walk and missions infrastructure.
We have a question about the payload here. Can we add a payload to the head of the ARM and communicate via Ethernet to the internal network of SPOT? In short, can it be treated as an external payload interface? Yeah, the form factor of that interface is a little bit different, but yes, if functionally it's the same interface as you get through the DB25s, except I guess we don't have the emergency stop sort of power disable feature on the gripper. We have a question about, are there plans for supporting grasping soft or fragile objects, such as fruit picking? I don't think we've built anything to date that would deal with a fragile object. Soft objects we do well with because we just crush them. But fragile objects, we probably at this point just crush. I think if you were developing an application through the API, Andy, correct me if I'm wrong, I think we can specify limits on gripper torque, gripper force there, or even use some of our impedance control features. That's right. So I think it's possible. It would take a little bit of investigation on our part and your part to make that happen. That's right. I think we're also going to supply some amount of torque limiting ability via the tablet API or the tablet interface. But as Al said, I don't think you probably don't want to pick up an egg with it right now. Can it grasp an egg? Okay, that's our next question. Yes, it can grasp an egg. It can also crush an egg. Okay, we have a question about possibilities to modify the gripper or the fingers towards the end of the ARM tooling. So in the short term, no. In the longer term, yes, it's on our roadmap of features to provide, but
we don't have a schedule for when we're going to actually be able to make that available. Again, if you have a specific, set of interactions that you think are particularly relevant, please talk to us, and we'll see what we can figure out.
So is there intention to provide a dynamic model of SPOT that can be used for study in university, or such as a ROS model?
No.
Yeah, I will add to that a little bit. The API provides a substantial amount of information about the robot's state, all of its joint locations, all of its joint velocities, and all those kinds of things. So I think you could, I think all of the information you want will be exposed over the API, but yeah, we're not planning to provide a ROS model.
Yeah, and the motivation for that is that, we're not providing low-level control through the API to users. And so there really is no benefit in having a highly detailed dynamic model outside of the robot.
So we've got a great question about integrating SPOT with AR and VR using 3D motion controllers. When connecting through the API, the question is, are we able to send target coordinates and rotations to the gripper, or would manual control require direct joint manipulation?
Yes, absolutely. We have, basically control of the arm is either through direct joint commands or through what we refer to internally as like drive the hand mode, which is just specifying, location for where you want the gripper and orientation for where you want the gripper. And we support doing that. Andy, correct me if I'm wrong. I think we support doing that both in body coordinates as well as a local world coordinate frame. So very easy to integrate an AR or VR system in your 3D controllers through an API.
Yep, that's exactly right. We provide control in both frames, and yeah, you send where you want to go, and we go there.
And that's the mode that supports the body obstacle collision avoidance that Andy had mentioned earlier.
Will this recording be available to participants? The answer is yes. All right, so we've worked through all of your questions. Did we want to say anything else, Al?
I think we're good.
Yeah, so overall, we have a question about pricing information, and that leads me to exactly what I was going to say next, which is you should talk to your sales rep. And I very much hope you buy the arm and enjoy using it. And this is just the first release, and I think we've already alluded to a bunch of features we're excited about launching next, with integration with lots of different things. And these things are just going to get better, but also, they're going to be informed by what you guys are doing with the robot and how we can make it work for your applications. So our team is really excited about going forward there.
I just want to reiterate what I said at the very beginning. We're very eager to be doing, for mobile manipulation, what we think we've been able to do for locomotion. And as Andy said, this is the first step in that process. And your feedback is going to be very, very helpful for us in understanding how to evolve these capabilities on the robot and make it really work in your applications and your problems. So yeah, please reach out to our sales team, and please look for innovative ways to use this kind of mobile manipulation capability in your settings. Great. Natalie, anything we didn't do?
Nope, I think that's it. We had one last question about specifications, and we do have a spec sheet available. So if you're interested in getting that, reach out to your sales rep. And if you don't have a sales rep, you can contact us at sales@bostondynamics.com, or contact sales through our website. So that is it. Thank you, everyone.
All right. Thank you very much, folks. Really enjoyed interacting with everyone this morning.